11.6 has two parts, three parts technically, the ratio test, the root test, and absolute convergence or conditional convergence. So we're going to do this video on the root test. We're going to call it 11.6a the root test. So here's what your book says. There are three cases. The first case says if we take the limit as n approaches infinity of the nth root of the absolute value of a sub n, that's a lot. But the limit as n approaches infinity of the nth root of the absolute value of a sub n, pause for a minute, notice that all of these are the same. Okay, so I'm going to write this differently in your notes. Don't write this down now. First of all, if it equals L, which is less than 1, then the series is absolutely convergent. If that limit equals L, which is greater than 1 or infinity, then the series is divergent. And if the absolute value equals 1, the root test is inconclusive. So then you have to pick something else. So let's write this a little bit nicer. So I'm going to use their notation and say the root test. So for the root test, let's make a note that the first thing we want to do is we want to take the limit as n approaches infinity of the nth root of the absolute value of a sub n. And then it's going to equal L. Let's say it equals L. And then we have three cases. Then case one, if L is less than 1, this implies that the series is absolutely convergent. Case two, if L is greater than 1, or if L equals infinity. L equals infinity is a terrible notation, but the limit would be infinity. So L equals infinity. Then this implies that the series is divergent. And then case three, if L equals 1, this implies that the ratio test is inconclusive. It doesn't mean, sorry, let me finish writing. It doesn't mean divergent. It means you have to try something else. So these are your takeaways. These are your notes that you need. So pay attention to that. Now I want to tie this into your reference sheet because you have a reference sheet that you'll have for your test. So look at this with me. So this is the reference sheet that you'll have for your test. You should practice using it. So down here we have the root test, and you can see that you're going to look at, you have given a series here, and you're going to look at the limit of the square root, the nth root of the absolute value of a sub n. If it's less than 1, then we have convergence. If it's greater than 1, then we have divergence, and you could add an infinity in here. And the test is inconclusive if the limit equals 1. So you don't have to memorize this because you can use this reference, but make sure that you know how to use it. Let's go ahead and look at a couple of these problems. Before we look at some problems, I would like to make a note that you can only take an nth root when there's an nth power. The root test only works when there's an nth power. So let's say you have everything to the power of 3, you cannot use the nth root there. So let's look at some problems and decide if the nth root applies or not, and then we'll come back to doing some. Okay, now these right here, 21 through 26, say use the root test. So you should be able to use the root test, but if you look at them right here, we have an nth power. Everything is to the nth power, so the root test will apply. Here you have -1, so the absolute value is going to kill that. And so you technically could say all of this to the nth power, so the nth root will apply. When you take the nth root, all of this is to the n squared power. So when you take the nth root, that n will cancel, and you're left with the squared. Here you could rewrite this to be the series of 2 over n to the nth power. Are you catching this here? So this you could rewrite to be the series from of -2n over n plus 1 to the fifth, all to the nth power. So the nth root's going to cancel out that nth power. And here you definitely have to an nth power. So you can see that that works on these cases. Now let's look down here. People want to use it on this problem. You can't use it on this problem because you don't have an nth power for everything. Let me this n right here doesn't have a power, and this has a power of n plus 1. You can't write it as a series to the nth power. But look, on number 31, you could use it because you have an nth power to the whole problem. So pause this video and decide which of these you could use the root test for, and then we'll come back to it. Hit pause, think about it. Okay, come back. 27 does not work. 38 does. 30 does not work. 32 does not work. 33 does not work. 34 does not work. Do you understand why? The reason 28 works is because we have the whole series to the nth power. In 34, we have a square root and we have a natural log, which do not have nth powers. In number 30, we have an n and we have a 10 to the n plus 1th power. That n has a first power. So when you cannot write it to a power of n, then you cannot use the root series. Okay? So now let's do a couple of these. Okay, so let's look at a problem. And it says the series from n equals 1 to infinity of -2 to the n power over n to the n power. Now this looks like a problem we could use the root test on, so let's do it. We have the series from n equals 1 to infinity. Let's rewrite it as -2 over n to the nth power. Now I would like to go further and write it as the series from n equals 1 to infinity of -1 to the n power. I'm sorry, -1, let's not write it that way. -1 times 2 all over n to the nth power. Because it's the first time we're using the absolute value in a series, let's write it that way. So we're going to take the limit as n approaches infinity, and we're going to do the nth root of the absolute value of a sub n. Now remember, when you look at your reference sheet, that the series, it says the series of a sub n. So that means everything except the series notation. So in here, we're going to put -1 times 2 all over n raised to the nth power in this absolute value. So this nth power and this nth root are going to cancel. If they don't, you cannot use the root test. So now we have n approaches infinity, the absolute value of -1 times 2 over n. Now think about the fact that the absolute value is going to kill the -1. And then we can just say the limit is n approaches infinity of 2 over n. Now, when we plug that in, we get 2 over infinity, which is 0. I'd like you to learn to use your reference sheet. So I'm gonna look at the reference sheet and pull that in here. Now 0 is my L, so I'm gonna say L equals 0, and I'm gonna come down here and look at my reference sheet. And my reference sheet says that my limit is less than 1. So when you go back up, that is my series for convergence. So that says that that means that the series, therefore the series from n equals 1 to infinity of -2 to the n over n to the n is convergent. You can write absolutely convergent because that's what it says. This implies convergent. It actually implies absolute convergence. Any of the above. As long as you got the word convergent in there, I'm good. But do you understand how to solve and how to use the reference sheet? So let's look at another one. It says the series as n equals 2 to infinity, and we have -1 to the n minus 1 over ln of n to the n. Now, the reason you can use this one, even though it's not an nth power, is because it's -1. So because we're doing an absolute value, that's not a big deal in this case. So I'm going to go ahead and label them using the root test. You should label which test you're using. We're going to say the limit as n approaches infinity, the nth root of the absolute value of -1 to the n minus 1 over ln of n to the n. I'm going to leave it like this on purpose. Now I'm going to do the absolute value first in this case. So the absolute value of -1 to any power is 1. So that's why that was not a big deal, because it was 1. Now in this case, we could write this to say the limit as n approaches infinity. The nth root of 1 is 1, and the nth root of ln of n is n. You could have written big parentheses around it and made it to the nth power, but if you take it, you can take the root of the top and the bottom separately, and then we end up here. So when we plug in infinity, we get 1 over infinity, which is 0. So that means my L is 0. When you look at your reference paper, that implies convergence. So we can say therefore, remember 3 dots means therefore, the series is convergent. Let's do one more. It says the series is n equals 1 to infinity, parentheses 1 minus n over 2 plus 3n to the power of n. This one is obviously a root test, in my opinion. The whole series is raised to the power of n. So we're going to say the limit as n approaches infinity, the nth root of the absolute value of the parentheses 1 minus n over 2 plus 3n, all raised to the nth power. Now my nth power and my nth root cancel. So I have the limit as n approaches infinity, and I'm left with the absolute value of 1 minus n over 2 plus 3n. Now my absolute value, my n gets very large, so it would be negative, so I'm going to keep my absolute value in this case. And if you think about when you plug in infinity of negative infinity over infinity, which is indeterminate form. So let's use L'Hopital's rule. The limit as n approaches infinity. Before I continue, you could have divided by the highest power of n in the denominator. Same thing. So the derivative of the top is -1, the derivative of the bottom is 3, and the absolute value of -3 is 1/3. So L equals 1/3, which is less than 1. Therefore, the series is convergent. Therefore, the series is convergent. I could do lots of these until I find a divergent, but I'm not going to. I'm going to let it go. So, um, I think I have one more that is divergent. Let's do that. One more. So we have the series as n equals 2 to infinity. We have the the top of the fraction is n over ln of n all to the nth power. So this is a root test. So we're going to say the limit as the n approaches infinity, and we have the nth root of the absolute value of n over ln of n all raised to the nth power. My nth power and my nth root cancel. Again, if they do not, you use the wrong series test. So we have the limit as n approaches infinity of the absolute value of n over ln of n. Now, if you think about your powers of your values for n, it's from 2 to infinity, so that's all positive, so you can lose the absolute value bars. So we have, I'm going to lose the absolute value bars, so I have n over ln of n. Now, when I do this, I have infinity over infinity, indeterminate form. So I have a fraction, I have a limit, I have an indeterminate form. We're going to use L'Hopital's rule, and we're going to say the limit as n approaches infinity. The derivative of n is 1. The derivative of ln of n is 1 over n. So that means that I really have the limit as n approaches infinity of n, which is infinity, which is divergent. Check your paper. L is greater than 1 or L is infinity, it means divergent. Therefore, the series is divergent. I hope that this helps, and I hope that you have a great day.